So the engineering problem we're going to be using is going to be a Couette flow with a rotating inner cylinder and a fixed outer cylinder. You can see from the side view that we've oriented the cylinder vertically along the z-axis. And you can see from the top view the expected velocity profile in the theta direction along the r-axis given an angular velocity of omega. And I've also defined the outer cylinder as r0 and the inner cylinder as r initial. I'll give you a quick briefing on the assumptions, but we're going to see how they affect the differential equation on the next slide. But steady state means anything that's changing with respect to time is 0. Symmetry across theta means anything changing with respect to theta is going to be 0. We're assuming no flow in the r or z direction, and the tube is infinitely long with closed off top and bottom, so we're not getting any additional force at those boundaries. We're also assuming that the fluid being used is incompressible and Newtonian, so we can use the Navier-Stokes in this system. And we're using the non-slip conditions to get the boundary conditions, which will be the velocity of theta is 0 at r0, and the velocity of theta is omega times the radius at r initial. And here are the momentum balance equations we're going to use. These are just the Navier-Stokes in cylindrical coordinates equations. You can find these equations in these coordinates in most fluid dynamics books, but if you try to use the transport phenomena book you probably have from your undergrad, you'll notice that they forgot about this term right here, which isn't really a small mistake to make. You'd think they figured it out by the second revised edition, but I guess not. So I just pulled it from the Shams fluid dynamics, and it seems to be correct from that one. We'll start off by solving for the momentum balance in the r direction. So like I said, anything that we've wrote down in the assumptions is going to be referenced here. And you can see which assumptions are used to cancel out terms and simplify them. We'll end up with this equation. And it's going to be an ordinary differential equation in terms of r and the pressure in the r direction. Moving on to the theta direction, we'll simplify the momentum balance. We'll use the assumptions that I wrote down in the first slide, end up with this equation. And you can already see this is in Euler-Cauchy form. And we can just start solving for it. We don't really need the z direction momentum for anything, but just for completion, we'll simplify this one as well and find out that the pressure in the z direction is dependent on the force of gravity. And we'll start solving for the momentum balance in the theta direction. We can already see that this is in Euler-Cauchy form, where a is 1 and b is -1. So we'll just plug those into the standard form. And we'll find that we have two real roots at m equals 1 and -1. And we'll just put in the solution form for it. So from there, we can start solving for C1 and C2. We can do that by plugging in the boundary conditions. We'll start by using v theta 0 at r0, and we'll get C1 in terms of C2, and then we'll do the same thing, but with boundary condition number 2. We'll get C2 as in terms of constants we know. We can plug everything back into the solution form of the Euler-Cauchy equation we just found. And if it looks messy, we can simplify it and just group constants together to find alpha and beta. And from there, if we were solving for pressure, we could just find the square of v theta. And so after finding v theta squared, we can plug that right back into the momentum balance in the r direction. And we'll get this equation, which looks a little weird, but we can just integrate it very easily. And this is the final equation for the pressure in the r direction that we'll get. And out of curiosity, I just decided to have some example inputs just to see what it would look like for the pressure and velocity in the theta direction in terms of r. And this is what it looks like.